Hi everyone, and welcome to the seventh video of this series. I had ended the last video by promising that I will demonstrate an analogy with the mechanical model. Now, in order to do so, um, we will assume that the resistance of the junction is a constant. That is, Gn is 1 by R, and here the resistance R is a constant. We take this for simplicity. Further, I'm going to assume that an external current source is keeping the current steady at I. That is, if an external current source is driving the current I, then I can write I to be equal to this right-hand side expression, which I wrote down in the last video. Also, this Gn which we had just written above. This is equal to 1 over R. Now next, I'm going to divide both sides of the above equation by I naught. And I'm going to denote I over I naught with a lowercase I. And further, I'm going to multiply both sides with E naught, which by the way is equal to H bar I naught over 2E. So if I make these if I if I make these changes, the equation which we will get is now further I can write this term. It can be written as the derivative with respect to the phase difference, and the derivative of E naught times 1 minus cos delta minus I times delta. And if you actually now look at this equation, this is actually this actually describes the motion of a particle with mass m. The mass m is given by h bar over 2e, the square of that times the capacitance, and it executes motion with the damping constant that is given by h bar over 2e, again the square of that times 1 over r, and it executes motion in the potential field that is given by this. Indeed, I can rewrite this in terms of the motion of the particle. So I can rewrite the above equation as follows. So this is the mechanical analogy that I was talking about. Now further, if I assume that I is equal to 0, that is, there is no external current, that is, there is no current I that is flowing, and for a small value of delta, I can write this equation. I can rewrite this equation as follows. And also because we have assumed that the phase difference delta is small, so I can write this term as just E naught times delta. And now if you divide the whole equation by this term, you can actually see that, and this is nothing, this equation describes the oscillation of a particle with the frequency of oscillation that is the same as the plasma frequency, which we defined in the previous video. Now you can go back to the previous video and check that this is the exact expression of the plasma frequency which we had defined. Next, in order to obtain a more full expression of the energy of the junction, um, we are going to do something new. So I want you to consider the term E naught I times delta. And I will take the time derivative of this term. Now for a constant current I, the lowercase I is constant with respect to time, which implies that the second term is zero. So we are left only with the first term. And we know that the time derivative of the phase difference is given by 2 EV over h bar. Also, E naught is given by h bar I over 2E. This implies that so the time derivative of E naught I delta comes out to be actually just V times I. This is actually the electrical power that is being delivered by the current source. So if to think of it, if we subtract this term, so this is actually the energy. So if we subtract E naught I delta from the energy expression of the junction which we obtained before, we are going to get uh, the total energy that is stored in the junction, because this energy is being delivered by the current source. So we need to subtract its contribution from the energy expression which we wrote before. Doing that, we will get. So to recall, the energy expression of the junction which I wrote before was this. And if I subtract this energy now, I will get the total energy as follows. And you can actually understand this expression in terms of, so we can call the first term as a kind of a potential energy of the circuit element actually. And the second term, it looks somewhat like the kinetic energy of a particle, half mv square. So we are going to call it the kinetic energy. This completes the discussion of the Josephson junction. So in the upcoming videos, I'm going to show you how qubits are formed using the Josephson junctions and what common architectures are actually used for qubits. I will see you guys in the next video.